systems for embedded. We're going to have good general purpose computing and domain specific computing and DSP. We could also never have succeeded. So how do you choose how narrow or wide the beam is? I think this is a key place to bring up Clayton Christensen. Now, many of you are already familiar with the core idea of Clayton Christensen's work, and it is a powerful idea, and it's a hopeful tale for startups. And the key lesson here is that, of course, we see once marvelous leadership tech companies that fall behind and become obsolete. But interestingly, it's generally not because they fell behind on the advanced technology. They fall behind because, in fact, they listen to their current customers too closely and too intensely. And those customers were saying, I want the same product I've been buying, but a little bit faster or a little bit cheaper or with this one innovation. And so they miss the technologies or the applications that serve fundamentally new communities of customers. They're so fixated on following their current customers. IBM got great at selling mainframes to very large companies. Mini computer makers got good at selling computers to a certain class of medium-sized organization. They missed the transition. IBM missed the transition to mini computers because they weren't listening to those local groups. The mini computer makers missed the PC revolution because they didn't even think that individuals buying these toy computers was an interesting market for them. And then you also recognize that the technology that it takes to serve the new customers is often quite low tech in the eyes of the established company. They sort of say, you know, it's not reliable enough. It's not fast enough. It's not, it doesn't do all of the things that our advanced customers are looking for. So why would I even bother? But then those low-end applications become so widely used that they grow in volume, and that growth in volume funds improvements. And so not only do they become high volume applications, but eventually it steers the investment dollars away such that those once low-end lousy solutions, you know, look back at the original IBM PC. That is a terrible computer. It's a terrible mini computer. It's a terrible mainframe. But over time, it displaced all of those things. It became better tech. But the better tech was the long-term impact. The real disruption came from finding the new customers who didn't demand such high tech, but they wanted something that was significantly cheaper, or perhaps more important, significantly easier to use in places where technology had been never used before. So there are particular lessons for deep tech startups that come out of this. Don't focus on displacing tech-savvy incumbents on their home turf. Don't go chasing NVIDIA into NVIDIA's cave. Look for places where new tech can transform cost or mobility or ease of use and can eventually drive huge volume over time. Find customers who can use a crappy product, where crappy is measured by traditional metrics. You know, maybe if you're building something for game use, you don't need 5 nines reliability, but it may be better in some other critical way. And timing is harder with the uncertainty on tech and uncertainty on user adoption. So stay lean. And I also recommend The Innovator's Dilemma. It's a great book that says a lot about how markets rise and fall more generally. I want to say a word about universities as well, because often deep tech does come from academic research. Researchers yearn for commercial impact. And so they're very eager to see their ideas be adopted be licensed, be used. They're often very eager to make the transition, at least for a while, from the academic setting to the product setting. Researchers routinely underestimate tech readiness. I remember this from the early days of MIPS. The original business plan for MIPS was, oh, we're going to take the Stanford MIPS chip, which was already running, and we're just going to fix it up a little bit, and we'll make that our first product. And then we'll move on to more ambitious things. And we just ran into so many little hurdles. We had a great review from Professor Mark Horowitz of Stanford to dispassionately assess the Stanford MIPS chip. And we just found so many holes that we would have such an underwhelming first product that we decided to completely discard the original Stanford MIPS architecture, memory hierarchy. Almost every concept almost every piece of the interpretation of the concept was discarded, and to start from an almost perfectly clean sheet of paper. So you have to understand, does your research, which may have pushed forward on certain really hard problems, does it leave you in a place where you can easily build on top of it? Or are you just taking the lessons learned, not the specific manifestation of the technology itself, forward into a company? Universities usually have IP rights for research results. So find the technology licensing office. Don't try to bypass them. And it's usually essential to include key inventors in the team. You can't just say, oh, well, I've read the patent, so now I know what to do. You don't. Very little of the intuition, the deep insights are embodied in a patent. They're in the people. So if you want to spin something out of a university, you need to include key inventors. And if you can include the professors who led the project rather than the grad students who may have been key inventors of specific components, that's better yet. The professors have, the full package. They've got the ability to abstract. They are well connected. They know how to speak to a broad audience. They have an impact on both the soft and the highly technical issues that relatively few grad students have. And there are, lots of resources around. I think that some of the people here have gone through NSF, National Science Foundation I-Course, which is a kind of startup boot camp, but it's aimed at university researchers. It's aimed at how to take the university perspective and turn it into something that works in a commercial domain. When you do license innovations from universities, there are some basic rules or guidelines. Do your homework, understand the tech yourself, understand the IP status, understand how you're really going to build a business around this, because universities are typically not thinking much about the go-to-market and what's the niche it's going to fill. Do it very professionally. Reach out to the technology licensing office. Start talking openly about what you might do. Involve the inventors. Gain technical insight and support. This is often welcomed by the technology licensing office. Share your plan about what you're thinking of doing so that you can get their feedback on what you're planning to do. Then you negotiate. You may look at doing an option agreement. Building a relationship with the university has many mutual benefits. Universities love it when they see the technology they developed turning into real visible deployments, and the company gets huge brand benefits by the association with the university. And there are obviously things not to do. Don't overpromise. Don't be excessively vague. Don't bypass the inventors. Don't treat it like a business deal. This is a close relationship you're building with the inventors and with the university. So we come back around to the big pitfall of deep tech products. Kind of to summarize, that you are often focusing on just one component. I'm building a new chip, or I have a new algorithm, or I have a new atomic structure, and maybe even a process to build that structure in small quantities. But you need to figure out how to leverage the component to build the rest of the system that needs change, because often you can't just slide that new chip into an old socket. You have to have new software. It's going to go into new boxes. You may need cloud service. You've got to build the rest of it so that it's available. And those things may be not just a simple evolution of the way those software or boxes or cloud services were done. They may want and deserve some fundamental rethinking. You also have to understand there's little motivation for the existing ecosystem to adapt. AWS will not immediately deploy your new chip in their servers until it is already mainstream. They are conservative. And so you don't count on AWS launching your product just because its ops per watt is better than what NVIDIA is offering. So you need to make sure that you can assign enough resources to build out the whole product. And that is going to compete with the resources that you put into the narrowly focused deep tech effort. Furthermore, you may find that while at the component level you have deep tech, your deep tech has really compelling benefits, but by the time you get to the system level, it's no longer a big difference. I mean, suppose I've got this super low power chip that I'm going to put into a system, but the system I build, that I have to build, uses 10 times as much power as the chip, that all the power is at the system level. And so your breakthrough technology might have made a 10% difference in the system level power. Is that a compelling differentiation? Unfortunately, no. And so you get to ask this skeptical question, this glass half empty question, which is, suppose I build my deep tech breakthrough and then I build the complete stack. What would have happened if I used conventional technology for the deep tech component? And one of three things may happen. You may say, no, it still just shines through. It's so compelling because of the characteristics of the deep tech component are not diluted by the complete stack. Or second, you may say, okay, I'm going to have to innovate a lot up that stack in order to get the benefits to shine through. That it is the combination of the benefits of the technical innovation deep in the stack and everything I did on top of it that make it a compelling system solution. Or finally, you may say, I did all this innovation at all these other levels, and in fact, the deep tech component is a small part of it. And in fact, I could reduce the risk, I could accelerate the time to market by omitting the deep tech component and using all of these innovations I've built up the stack. And that's an even better, cheaper, faster to market, lower risk solution than before. Now, I haven't often seen people make that pivot. They fall in love with their deep tech, but it is a really good question to ask along the way to make sure that the deep tech really matters, even to your own solution. So let's talk about a little bit about real world cases, because we think about these deep tech wins you see in the market, but sometimes they represent years of trial and failure or near misses. Even iconic successes are built on disasters. NVIDIA, founded in '93 by Jensen and Chris Malachowski and Prem. Their initial mission was chips for 3D graphics in video games. They built their first chip, their first accelerator, the NV1. It failed. It failed because it didn't have key software support, the DirectX protocol that had sort of come out in that same period. And they had a design win at Sega for the Dreamcast, and they also lost that. And they had to go through downsizing from 100 people to 40 people. Really painful. Their first successful product came in the next generation after that, in the Riva 128. At that point that they started to sell that, they had 30 days of cash left. But they quickly accelerated from that point. They were in the right place at the right time after two major misses. So they went public a couple of years after that. And going public in 6 years is pretty good. Going public in 6 years after major disasters is better yet. We think of SpaceX as a great success, but and they had this early vision of 10x reduction in space launch cost. But in the critical period, at year 4 to year 6, it was nothing but disaster. They had failure after failure on their launches, and they didn't have a successful launch until 2008. And they were heavily funded by NASA. NASA was rooting for them from the beginning, and at the point where they were getting near to their Falcon 1 launch, they got this $1.6 billion contract. This is not a conventional startup. This is not conventional funding. And it's almost a mistake to look at SpaceX and say, yeah, that's my model for a startup. It was really a government program to a significant extent. Let me talk a little bit about Tensilica, because this is a more detailed view, because I was obviously there from the beginning. So incorporated in 97. And the way we stated our mission from very early on was to become leading provider of application-specific microprocessor solutions by delivering ASIC-based cores, application-specific IC cores, and matching software tools. And pretty rare among tech startups, we didn't pivot. I mean, you could apply that today to what the Tensilica group at Cadence is doing, and it would be recognizable. Initially, it was just me for the first couple of months. Then Bernie Rosenthal left Synopsys. Harvey Jones, who was the chairman of Synopsys at that time, became very interested and got on board. And then there was an absolute dream team of people who joined in the first few months. Beatrice Fu came in as head of engineering. She's here on the call today, and we'll be hearing from her later. Say hello, Beatrice.
Hello.
Thank you. But other great people, Gulbin, Ashish Dixit, Dror Maidan, Albert Wang, all representing the key technical domains: microprocessor architecture experts, EDA experts, compiler experts that were needed to put this together. And so there was a long and really painfully slow ramp of customers and new technologies and spreading use, because in fact, we went pretty broad, pretty early, probably too broad in retrospect. But we eventually got adoption across many kinds of embedded products, routers and switches and storage units, and into PCs and into cell phones in a big way, and into cameras. A really broad cross-section of all kinds of silicon platforms, with a heavy emphasis on DSP. Audio DSP was in some ways the killer app that made this whole thing work, but also quite strong in communications DSP and in video DSP, as well as in a range of different niche roles. Acquired by Cadence, it was about a $400 million deal, which actually made it the biggest exit of a venture-backed company in the semiconductor space in a decade. So it was really a pretty big win, but 1997 to 2013 is 16 years. And now it's a widely successful business unit inside of Cadence. The use of it has continued to broaden. I think there are 40 or 50 billion Tensilica cores out in the wild today. And we had this core pitch, and this pitch really became, I think, one of the the iconic stories that was used consistently over much of the history. And the core idea was that a chip architect would start with an idea of what they're trying to do. They need more compute. They need more memory bandwidth. They need more efficient control. They need to make everything in their chip more software programmable. And so they build a unique new microprocessor by selecting from a menu or making explicit description of the functionality they need in the instruction set. And that goes into this magic box called the extensive processor generator, which creates the full hardware design, including all of the whole product environment for turning that into a block in the customer's chosen semiconductor process technology, and a complete suite of software. The compilers, the debuggers, the simulators, the ports of the popular operating systems. In a sense, you'd say everything that you would want from an ARM core that you get because the ARM instruction set is stable and fixed and immutable and has a stable, fixed, immutable collection of compilers, debuggers, simulators, and operating systems, but now created to order in minutes from a high-level specification that leads ultimately to the incorporation of that hardware and that software environment into a chip. And this was a formula that worked well. It was perhaps too diffuse and required too elite a customer in some ways, but as we enriched the product, we found verticals that made sense. And the select options from a menu, rather than get into the nitty-gritty of instruction set design, became more and more popular, particularly around things like audio DSP, video DSP, and communications DSP. And they became standards. So Tensilica became by far the most widely used DSP on the planet. You know, TI was famous for DSPs, but Tensilica DSPs have outshipped TI DSPs by orders of magnitude, I think, at this point. So it describes what was the input, what was the magic, what were the outputs, what were the benefits. Time to market, efficiency, ease of software programmability in areas where software programmability had not been possible before. Let's also look at NVIDIA, because I've studied, at least as of a few months ago, what the state of three really high profile and in their way extremely successful NVIDIA killer startups have looked like. And interestingly, they're all about the same size. They've all gone through similar valuation trajectories, but they've all taken somewhat different approaches. Cerebras, which is based in the Bay Area, focuses on ultra high-end wafer scale integration of neural compute and memory. And their target customers being the national labs, really, very high-end configurations. Their business model is the sale of systems plus cloud access. Their software infrastructure is aimed at both training and inference, and they have a range of optimized models. The standard models are available, and they claim some, incredibly huge performance numbers, in part because they have incredibly huge chips, this size, representing hundreds of thousands of teraflops. The revenue is generated or is dominated by the UAE G42 AI holding company, which has made a prepayment of $1.4 billion this year for future systems. They hope to go public soon. They're very, very high end. And so one key issue is it's very high entry cost. You really can't do anything with them for less than a few $1 million. And as a result, they have very concentrated customers. Having one customer, which is really a government entity that's using this as a way to kind of ride the hype wave associated with AI, is a little worrisome. SambaNova, another great company, key people coming out of Stanford. They are doing a kind of configurable array of computing units. It's really a data flow based approach. They also follow what has to be the standard business model for this sort of thing. You don't sell chips, you sell systems, you sell subscription, you sell access to servers running it. Their peak chip performance is a little bit is significantly lower because it's not so huge a chip. They have significant revenue. The estimates are $75 to $150 million range. It's a mixture of hardware and inference services. Their key issue probably is that they are competitive with NVIDIA in terms of what is the cost per op delivered, but they don't have NVIDIA's scale. So their infrastructure is not as mature, and they can't deliver a fundamental new platform at the same pace, because with only 450 employees compared to how many tens of thousands at NVIDIA, they just can't have as much product development overlap. GraphCore has a lot of things in common with SambaNova. They are targeting training and infrastructure. They are not so much focused on providing a live service, but in sales of hardware, cards, racks, system. They have a software infrastructure. Their peak chip performance is more modest. It's actually pretty modest compared to NVIDIA's latest. There's less information available to them because they were actually acquired by SoftBank last year for about $500 million. And up until that point, they had had minimal revenue. I think they have fallen behind on performance. They haven't provided the same level of cloud accessibility. So they've gone back behind a wall, and it's harder to see what's going on there. But if you look at the funding history, they all grew up into comparable levels of valuation and comparable levels of funding raised. They all raised in the neighborhood of $700 to $900 million so far. That's pretty serious money. That's an extreme form of deep tech takes more capital. So what are the outcomes? Successes can be bigger, but the investments and the risks are higher. It's a high stakes game. Making the tech progress visible supports all these goals. That is, from even before you announce a product, announcing the areas of technological breakthrough can make sense. Yes, you have to be secretive, but in deep tech, it's so rare to pull together the kind of people necessary to do this that I don't think you have to be as secretive, because fewer people are even going to be tempted to copy what you're doing. And you can talk about the technology progress without really revealing either the details of what you've done to make the tech happen, nor what your business plans are. It makes it more likely that you'll be acquired for the team and the technology than for the market momentum, because market momentum may take many years to do. In fact, if I look at Babel Labs, I was surprised at how early in our history, after just 2.5 years, that we were a candidate for acquisition. And it was all because the team and the technology fit fit a need in the market more than Cisco wanted our product line because they wanted to continue to sell that as part of their product line. I would say that patent portfolios are nice. They are valuable, but they rarely are consequential in the outcomes. They play more a symbolic role than either a defensive role, and certainly they don't typically get used by startups in an offensive role. Very few startups would be well served to go start suing big companies over patents. It's just a distraction from what their real job is, which is to build a product. So patent portfolios are good, but I think they're more about marketing than they are about IP protection, ironically. Now, the patent portfolio may be quite important to an acquirer because they do have the kind of business where they need strong defensive properties. And if they're going into a broad new area strategically, they will want to populate it with enough patent protection in order to cause their potential enemies to think twice. Integration of a startup into the acquirer can be tricky because the acquirer has different products and different markets in mind in many cases. And so it may require a rapid pivot of what is the end application it goes into. And as a result of these things, particularly because of the interest in acquiring in the team and the technology, the acquisition interest may come ahead of market traction. I think that this lesson here on GraphCore is an example of that. SoftBank was interested in having the technology play, interested in the team, not because they wanted the $3 million worth of revenue. So why do you do a deep tech startup? You do it because you have a unique handle. You have expertise. You know how to do something that few people know how to do. And that's a potentially huge asset. You build it because you want to not just have a little bit of impact, but by investing in tech, you have a chance to have a really broad impact. It's not easy, it's not probable, but you often have no way of getting there if you don't have deep tech in the portfolio. And you have the opportunity to transform a product segment. You can reach many new users. You can reach new patterns of behavior. You can increase the whole impact of a segment because it's powered by a new class of technology. You can say, I'm just trying to think of something off the top of my head. The availability of GPS, just one deep tech idea, didn't really come from a startup, but one deep tech innovation transformed how we use cell phones. So it changed the impact of cell phones because it allowed cell phones to be used in many new applications in ways that no amount of software could otherwise create. And why do it? Because of the people you get to work with. The act of collaborating on a hard problem over years with really smart, motivated people is a huge satisfaction. And working in that kind of environment, working when you have an aim of changing the world is uniquely satisfying. So the takeaways from this: deep tech ventures tackle fundamental technical innovations. And as a result, they're harder, slower, and riskier than most other ventures. The risk is offset by the potential for higher long-term impact. You have to keep an eye on whether the transformation of the ecosystem magnifies the value that you're doing somewhere deep in the technology, or it dilutes it, and make smart decisions about how you approach the rest of the product, the whole product, the ecosystem. So you have to do both breakthroughs in the tech, and you have to do full system thinking. And you get to work with great people. You need great people. And you need to be able to find that balance between what the great people working on the deep tech can do and what you can get other great people to work on that focuses on what's the ultimate application, what's the product market fit, what's the customer confirmation of value.